So I think to this audience, people are more familiar with towers of function fields. So, but I will talk about towers of Ramanujan graphs. And at the end, I hope I can compare both. Okay. Okay. So let me start with the towers of function fields. Okay. So evaluating rational functions at rational points on a curve defined over a finite field of Q elements. Gopa in the 1970s introduced algebraic geometry codes. Okay. So they give rise to long linear codes with good parameters, beating the Gilbert-Wassermann bound for non-primes Q at least 49, except possibly for Q equal to 125. This was the results of Schwarzman, Vlado-Zink, and Garcia, Stichnoth, Bassa, and Wieland. So in order to get good algebraic geometry codes, one needs curves with many rational points. But the number of rational points, grows when the genus grows. So it's better to compare the ratio. So for a given curve, so we fix the finite field of Q elements. So given the curve X, well, we use the NQX to denote the number of rational points on the curve. We divide by the genus, and we let genus go to infinity. So Ihara introduced this quantity called AQ by taking lim sup of this ratio. Okay. And Drinfeld-Vlado showed that an upper bound for AQ is root Q minus 1. So in the case Q is a square, and Ihara and independently Schwarzman-Vlado-Zink exhibited infinite families of curves achieving this upper bound. Therefore, when Q is square, one knows that AQ is equal to root Q minus 1. Okay. So the curves they use in their construction are the reductions of the Shimura curves and the elliptic modular curves. Okay. Then in order for this to be useful to really to construct AG codes, one would need to have explicitly given the models for the curves and then go from there. So in 1995, Garcia and Stichnoth gave the first explicitly and recursively constructed infinite family of curves over this given field, FQ with a square cardinality. Okay. So their family is asymptotically optimal, means that the limit achieves the bound to root Q minus 1. Okay. So in their tower, their construction is very beautiful. Okay. They start with the projective line over FQ, okay. And then they begin to build up. And the way they build up is that each curve is a complete intersection. Like the nth curve, you take n variables and you have n minus 1 equations, except that these n minus 1 equations are all the same polynomial, and using only 2 variables, each time you only use consecutive variables. Okay. So from this, it's very clear that xn plus 1 is a cover of xn. Okay. So in their infinite family, it's a sequence of covers, which we call a tower. Okay. And since then, many people have been trying to find out the explicit families. There are many people, including those sitting in this room. I will not risk by giving names. So, and also people try to find towers using computer search. So it turns out that all the known explicitly and recursively constructed towers of asymptotically optimal curves, they are all shown to be modular by L-keys, basically, okay. Which means that you can show that they all come reductions of elliptic, Shimura, or Drinfeld modular curves. Okay. So therefore, L-keys conjecture that this should be the case when we have when Q is a square and we have recursively explicitly constructed optimal towers. Okay. So this conjecture is still open. And when Q is a non-square, and the story is quite different. So first of all, one doesn't know the precise value of AQ. Okay. So when Q is a prime, Sayre showed that has a lower bound that's constant times log 2p, and that this is still the best known lower bound for prime p. Okay. But if we do not think about prime p, but think about the higher odd powers, and nowadays there's very good lower bound, which I call the BQ for the AQ. And also there's explicitly recursively constructed towers asymptotically achieving this lower bound BQ. Okay. So the first such lower bound is given by Zinc for the case Q equals P cubed. Okay. So his bound has the shape twice of P squared minus 1 over P plus 2. So he obtained that using degenerations of modular surfaces. Okay. So if one replaces P by P to the R, so we're still looking at when Q is a cube, then Becerra, Garcia, and the Stich-Nath obtained bound for this kind of prime, P to the 3R, just by replacing P by P to the R. Okay. So they are explicit towers, which was constructed by van der Geer and van der Vloot when Q is equal to 2 cubed, and the remaining ones by the Becerra, Garcia, and the Stich-Nath. Okay. So for the prime power in general, but not prime, so a very exciting development was the last year. Garcia, Stich-Nath, Bassa, and the Bielen, they obtained a best-known lower bound with the following shape. Okay. So if you write your Q as P to the 2n plus 1, then this bound is 2 times P to the n plus 1 minus 1 over P plus 1 plus a little bit epsilon. Okay. So I should say that when m is equal to 1, so namely Q equal to P cubed, this is the same as the Zinc bound. But otherwise, this is better than their previous Q bound. Okay, so this is indeed the best known lower bound. And they also constructed explicit asymptotically optimal towers using Dreamfield modules of rank at least 2. So I'm glad to hear that although Henning is not giving a talk, but Alp and Peter will be discussing this piece of work. It's really beautiful. Okay. So, as we said, to construct good AG codes, one needs curves with many rational points. And in general, the place where it records the number of rational points or over any extensions is the zeta function. So if I start with a curve, say smooth irreducible projective curve of genus G, defined over this finite field Fq, so one can define the zeta function, which counts the number of points of this curve, this V should be x, over any degree n extension. So we formally form this, the number divided by n times u to the n, then exponentiate it. So this zeta function is known to have infinite product over closed points, and each factor is 1 over 1 minus u to the, degree v. Okay. And this zeta function is known to be a rational function. The denominator is 1 minus u times 1 minus qu, which is the same for all curves defined over q. But the numerator gives more information about the curve. So it's a polynomial with coefficients z and has degree twice of the genus. And the famous Riemann hypothesis says that all the roots of the numerator have the same absolute value. In this case, it's q to the minus 1/2. So this was proved by Hasse for elliptic curves and the Weil in general. Okay. So this is about the information on the curve side. Then next, let me move to the combinatorial objects. Okay. So I'll talk about the zeta function attached to a graph. Okay. So this is what we call the Howard zeta function. So this actually started from the Selberg zeta function, which Selberg defined in 1956. And that zeta function is to count geodesic cycles in a compact Riemann surface, which is obtained by taking the upper half plane modeled out by torsion-free discrete co-compact subgroup gamma. Okay. And we know that the upper plane can be written as SL2R mod SO2R or PGL2R mod its maximum compact subgroup. So this Riemann surface can be seen, well, as the on this double coset. Okay. So what Ihara was trying to do in 1966 was that he replaced this field, real field R, by non-Archimedean local field with Q elements, its residue field. Okay. So he considered the double coset of this kind, PGL2F modeled out by its maximum compact on one side, and the other side by torsion-free discrete co-compact subgroups. So he defined the zeta function, in this case, just mimic what Selberg did. And then Sayre pointed out that what Ihara did actually really works for all the graphs. So this is the definition I'm going to talk about now. Okay. So let's start with the connected undirected finite graph. Okay. So what I call a cycle is what combinatorics call a closed walk. Okay. So it has a starting point, also has orientation. So if you have different starting point or different orientation, it's counted as a different cycles. So what we are interested in counting is called a geodesic tailless cycles, which has a shape of this loop, like what you would think of. Okay. Now, the other side that I show you is a cycle with tail. So if I start from the end of the tail and I walk around it, so I do get a geodesic with no backtrack. But if I change the starting point, then you see that there will be a backtrack. So we don't want the cycles with tail. Okay, we only want the cycles without tail. Okay. So the Ihara zeta function for the graph counts the number of the geodesic tailless cycles of given length n. So you see that the form of definition looks exactly like the way we define the zeta function for curves. Okay. And it also has expression as an infinite product. Okay. And what plays a role of prime is the equivalence class of the primitive geodesic and tailless cycle. So a cycle is primitive is not if it is not obtained from another cycle by circling it more than one round. That's obvious. And the equivalent means that if I shift the starting point, that's regarded as equivalent. So when I look at the equivalence class, that means that I really look at the shape, but including orientation. If it's opposite orientation, it's another one. Okay. So, and the factor is 1 over 1 minus u to the length of this cycle. Okay. So here I'd like to compare this expression with what we did for the curve. Okay. So when we compare a graph with a curve, we should think of that a cycle corresponds to a point. Okay. So in case of curve, one consider close points. So a close point means that you take a point and look at the Galois orbits, you put it together, that's a fat point, that's a close point. So in case of a primitive cycle, is that equivalent ones are that you're shifting the starting point. So that's also sort of like conjugate. Okay. And for the case of curves, here we have the degree. Degree is the number of points in this Galois orbit. And for the case of curves, if this curve we look at is primitive, then the number of curves equivalent to that is exactly the length. So this expression here is exactly like what happens for the curves case. Okay. So when we look at the zeta function for curves, we know that it's a rational function. So how about the graphs? Okay. So Ihara showed that if this graph is deregular, then this zeta function is also a rational function. So the numerator is 1 minus u squared raised to the power of Euler characteristic. So the numerator gives you topological information about a graph. And denominator is determinant of identity matrix minus adjacency matrix times u plus d minus 1 times u squared identity. Okay. So to each graph, we associate an adjacency matrix. This adjacency matrix has its rows and the columns parameterized by the vertices. So the UV entry records the number of edges between U and the V. So when you see this adjacency matrix, it's the same as seeing the graph. Okay. Now, since this adjacency matrix is symmetric because our graph is undirected, and so we know that for the real symmetric matrix, all its eigenvalues are real. So I can align them from large to small. And because our graph is regular, d-regular, so it's easy to show that the eigenvalue sits between d and the minus d. And the d is an eigenvalue because all one vector is an eigenvector because each row adds up to d. And it has multiplicity 1 because we assume the graph is connected. Yes? D-regular means that each vertex has exactly d neighbors. So it's very uniform. Everybody has d neighbors. Okay. So if I just look at denominator here, because I'm taking determinant, I may as well assume that this adjacency matrix is diagonal with eigenvalues on the diagonal entry. So this determinant can be rewritten as a product over the eigenvalues, 1 minus lambda iu plus d minus 1 times u squared. Okay. So denominator here gives you the spectral information about the graph. So well, I already explained that d is eigenvalue, which is achieved once. And minus d is an eigenvalue if and only if the graph is so-called bipartite. Okay. So we know very well that about the eigenvalues d and the minus d, so they are called the trivial eigenvalues. All the remaining eigenvalues are called the non-trivial eigenvalues. Okay. So we know that the zeta function for curves, they satisfy the Riemann hypothesis. How about the zeta function for graphs? Okay. So on the numerator here, I have 1 minus u squared raised to the Euler characteristic. But this Euler characteristic actually is a negative integer. So this 1 minus u squared, this term actually goes to the denominator. The zeta function is 1 over a polynomial. Okay. But then we know that, well, the poles of the zeta coming from 1 minus u squared are plus minus 1, so we consider this as a trivial pole. Okay. And also, another kind of trivial pole comes from trivial eigenvalue, when lambda is equal to d and the minus d, and we will have a trivial eigenvalue plus minus 1, and the plus minus 1 over d minus 1. So those are the trivial eigenvalues. Those are trivial poles for the zeta. So what we are interested in is the remaining non-trivial poles. Okay. So we say that the zeta function satisfies the Riemann hypothesis if all the non-trivial poles have the same absolute value. Okay. From the construction, this same absolute value would be d minus 1 raised to the minus 1/2. Okay. So if you go back, look at the denominator here. So if each quadratic factor here have the roots with the same absolute value, this is equivalent to saying that the discriminant, this lambda squared minus 4d minus 1, is less than or equal to 0, which is the same as saying that absolute value of lambda is bounded by 2 root d minus 1. Okay. So when this happens, we say that this graph is Ramanujan graph. Okay. So in other words, if we pick up a d-regular graph, then the zeta functions do not always satisfy the Riemann hypothesis. Those satisfy Riemann hypothesis come from very special kind of graphs, which you call the Ramanujan graphs. Now, there's another way to describe the Ramanujan graphs. That's from the spectral theory of the graphs. Okay. So this is a well-known, very famous theorem by Lubotzky-Phillips-Sarnak, which says that if we take a family of d-regular graphs, they are undirected, say, okay, and I look at the largest non-trivial eigenvalue, which is, say, lambda 2, okay, I look at lim inf as the size goes to infinity. So they show that this lim inf is at least twice d minus 1. And for the same family of graphs, one can ask the symmetric question. How about the other end? I look at the smallest non-trivial eigenvalue, and I consider lim sup. whether whether that thing is less than or equal to minus twice root d minus 1. And the answer is that it's not always the case, okay? But it holds under minor assumption. For instance, if the length of the shortest arc cycle in the graph turns to infinity as the size goes to infinity, or we allow short cycles, arc cycles, but there are only very few of them, then this will hold. In particular, if graph is bipartite, then it doesn't have any arc cycles, then this will hold. Okay. So the meaning of these two bounds, 2 root d minus 1 and the minus 2 root d minus 1, is that if we consider the interval from minus 2 root d minus 1 to 2 root d minus 1, this interval is a spectrum of the d-regular tree. So the d-regular tree is a universal cover of any d-regular graphs. Okay. So the above two statement says that if I pick a very large d-regular graph, it's very likely that the largest non-trivial eigenvalue will go outside to the right, and the smallest non-trivial eigenvalue will go to the left. Okay, they'll go outside of this interval. When this thing doesn't happen, then that means that all the non-trivial eigenvalues have absolute value bounded by twice root d minus 1, and that's precisely the Ramanujan graph. So from the spectral point of view, a Ramanujan graph is spectrally optimal. Okay. So if they are used as communication networks, then they have very nice properties, like a large expansion constant and very quick mixing, and also has small transmission delay, and so on. Okay. So let me just give you one example of Ramanujan graphs. This is what I want you to take home with if you don't remember anything else about this lecture. So, so this Ramanujan graph everybody knows, which is what? A sucker. Very good. So if you look at each vertex, it has 3 neighbors. So this is a 3 regular graph. Okay. So if I strategically add one more line so that this becomes 4 regular, and I put a carbon at each vertex, this is the famous molecule called it's famous fullerene molecule called a C60. Okay. And also this Ramanujan graph is a Cayley graph based on the group PSO25. Okay. So a Cayley graph means that we construct a graph, its vertices are elements in the group, and the neighbors are this element, well, right modification by the chosen generators. Okay. In this case, the set is translation by 1, translation by minus 1, and the inversion. Okay. So I hope that you remember this graph. Okay. So sort of like the case for the codings, if we want our graph to be useful, we would like to explicitly construct it. So the explicit constructions of Ramanujan graphs were first given by Lubotzky-Phillips-Sarnak and independently by Margulis. Okay. So in that case, the graph is a p plus 1 regular, where p is a prime. Okay. So when you look at a graph whose valency is a prime power plus 1, and this kind of a regular tree can be given a structure as a homogeneous space. So the p plus 1 regular tree, well, can be, the vertices there can be identified as a PGO2 QP mod its maximum compact subgroup. Okay. So each coset represents a vertex. Now, this its maximum compact subgroup is not a normal subgroup. So normally, to represent these vertices on the tree, you usually when the vertices are the cosets, you cannot represent them using a group. But in this particular case, we can represent this the vertices using a group lambda. So this group lambda is coming from a special kind of the points on the Hamiltonian quaternion group. Okay, so I will not bother you by its definition. Just think of that. So we strategically pick some kind of Hamiltonian quaternions. So it's A plus BI plus CJ plus DK, where A, B, C, D are integers. Okay. And this infinite tree actually is a Katie graph. And the generating set we choose are those elements in the group which have reduced norm P. And they are P plus 1 of them. And also this set is symmetric. So we do get undirected P plus 1 regular tree. Okay. So the advantage of having this, the points in this group lambda having integer coefficients is that then we can take a different prime, we can do reduction. Okay. So I can take a different prime q not equal to p, and I do reduction modulo q. So I have the group modulo q, and I have generated modulo q. So then I come up with a finite graph. So the cosets will be the lambda modulo the kernel of the reduction. Okay. So Lubotzky-Phillips-Sarnak gave a very explicit description of this quotient group. So it's either PGL2FQ or PSL2FQ, depending upon whether P is not a quadratic residue modulo Q or P is quadratic residue modulo Q. Okay. So in other words, the graph obtained by the modulo Q is a nice Katie graph defined on a familiar kind of groups. And the question is to show that they are really Ramanujan graphs. Okay. So why is it Ramanujan? Okay. So the vertices of the graph is lambda modulo the kernel of the reduction. And the lambda itself is a PGL2QP mod its maximum compact. So we can think of these vertices of the graph as representatives of some double cosets for PGL2QP. Okay. So because of the nature that this group lambda is coming from this Hamiltonian quaternion, so one can use the strong approximation theorem to show that this double coset representative for PGL2QP actually is also double coset representative for delic points on the quaternion group, okay, of this Hamiltonian quaternion group. Okay. So the choice of this lambda Q now becomes the choice of maximum compact, choice of compact subgroup depending on Q. Okay. So with this kind of description, then when we look at eigenfunction on the graph, then if it's non-trivial, I can think of that it's an eigenfunction. It's actually automorphic form, okay, on this quaternion group. And the adjacency operator is nothing but the Hecker operators acting on these automorphic forms. Okay. So we are interested in the non-trivial eigenvalues. So those will be the non-trivial eigenvalues of Hecker operator at P acting on such kind of automorphic forms. And there one uses the Jacob-Leibniz correspondence to reinterpret those automorphic forms as a way to curse forms. And there we have the very famous result by Shimura saying that this eigenvalue of Hecker operator does satisfy the Ramanujan bound, which means that bounded by absolute value bounded by twice square root of P. So this kind of graphs are Ramanujan. Okay. So the key thing is this setup. So this setup says that we can obtain many other kinds of Ramanujan graphs. I can change the quaternion algebra. I can change the congruent subgroup. In particular, if the congruent subgroup is chosen to be one containing the other, then we actually get a tower of the graphs. Okay. Or one can change the field from Q to a different field, like function field, where the Ramanujan conjecture was proved by Drinfeld. Okay. So we get lots of Ramanujan graphs this way, infinite family of Ramanujan graphs. Okay. Okay. So I would like to also spend a little bit of time explain the connections between graph zeta function and the curve zeta function. Okay. So I said that when Ihara started, he took this F to be a non-Archimedean local field with Q elements in its residue field. So we mod out by its maximum compact. So this is a Q plus 1 regular tree. And on the other side, we can mod out by torsion-free discrete co-compact subgroup. So then we get a finite graph. Okay. Now, in particular, say if I take this field to be QP that we have seen, okay, and so this OF will be just the ring of p-adic integers. So I'm going to show you, well, how to choose different kinds of this group gamma. Okay. So we can choose this gamma as coming from the definite quaternion algebra, which defined over Q, which ramifies only at two places, infinity and another prime L, not equal to P. Okay. And this gamma, we will choose it to be the almost integral points, except that we allow P in the denominator. Okay. So we look at the non-zero elements and we mark out the center. Okay. So, so this kind of gamma, well, gives a discrete co-compact subgroups. Okay. Now, this group will be torsion-free if L is count to 1 modulo 12. Okay. So let's just choose this kind of L, count to 1 mod 12, and then look at this kind of graphs. So this kind of graphs, they are Ramanujan graphs. So this is another family of Ramanujan graphs where it's not a tower, because the group for each graph I change the group coming from different quaternion algebra. Okay. But the interesting thing is that I just look at this graph. Okay. So I look at its zeta function, and its denominator is determinant of 1 minus adjacency operator u plus pu squared identity. So I remove the factor coming from the trivial eigenvalue. So then what's remaining are those corresponding to the non-trivial eigenvalues of this graph. Okay. And it's a result of Eichler-Shimura saying that this polynomial actually is the numerator of a curve that is the modular curve x naught L modulo P. So in other words, what I want to show is that there are some kind of graphs. If you look at its zeta function is identical with the zeta function of some curves. So there's some connection. So this kind of the graph we just chosen here, its cardinality is 1 plus the genus of the modular curve x naught L. And that thing is called it is equal to the class number of this quaternion algebra, DL. Okay. And on the other hand, from the combinatorial side, if I have a graph, I look at the number of spanning tree inside this graph, and that number is called the class number of the graph. Okay. Now Hashimoto has the following theorem, which says that if you take this graph, which is Q plus 1 regular, you look at the denominator of its zeta function, and you remove the factor corresponding to the trivial eigenvalue. So then you evaluate that at u equal to 1. And so this is special value of the zeta function at u equal to 1. And he showed that that number is equal to the class number of the graph times size of the graph. If we apply this result to the graphs constructed using the special kind of quaternion algebra, then on the left-hand side, we have the class number of the graph times class number of the quaternion algebra. Right-hand side, remember that this quotient is equal to the numerator of the curve, or the modular curve. So when you evaluate it u equal to 1, that gives you the size of the Jacobian of x naught L at fq. And the size of Jacobian is precisely the class number of the function field of the curve x naught L over over fp. So this is a very beautiful identity of a class number times class number equals to a class number. So remaining time, I'll talk about the more recent development about the Ramanujan towers. Okay. So I talked about the Ramanujan graphs. Okay. So I talked about the regular graphs. Now how about the biregular graphs? Okay, so if we consider the graph where the valency, there are two kinds. So one kind of vertices has C neighbors, the other kind of vertices with the D neighbors. So this is called a biregular bipartite graph. And its universal cover is a biregular bipartite tree. And in the paper with Soleil, we show that the covering radius for the spectrum of the universal cover is root C minus 1 plus root D minus 1. Okay. And for any finite CD biregular bipartite graph, the trivial eigenvalue is plus minus root CD. Okay. So one also has the similar result like Alon-Popana theorem. So if we take an infinite family of CD biregular bipartite graphs, okay, then one can show that the lim-inf of the largest non-trivial eigenvalue is greater or equal to root C minus 1 plus root D minus 1. So namely, so in this case, again, you see that the largest non-trivial eigenvalue tends to go outside of the radius of this universal cover. Okay. And because if you consider the bipartite graph, the other side is symmetric, so we also have the lim sup of the smallest non-trivial is less than or equal to the negative of this thing. Okay. So therefore, one calls a biregular bigraph Ramanujan if its non-trivial eigenvalues have absolute value bounded by the covering radius of the universal cover, namely root C minus 1 plus root D minus 1. Okay. And some combinatorics like Victorson and company, they also use this to define the Ramanujan graph for any irregular graph. Okay. So namely, the non-trivial eigenvalues in absolute value are bounded by the covering radius of its universal cover. Okay. So I talked about the infinite families of Ramanujan graphs constructed using number theory. There the tree has valency Q plus 1, where Q is a prime power. So all the Ramanujan graphs constructed this way will have the valency, which is prime power plus 1. And it's a natural question to ask that, well, if I just pick up any positive integer D, whether there is an infinite family of Ramanujan D-regular graphs. Okay. When D equal to 2, well, you just take the cycles. So that thing is obvious. So we assume D at least 3. Okay. So before we answer this question, here Joe Friedman has shown that so a random large D-regular graph is very close to being Ramanujan, okay, which means the following. So the Ramanujan bound is twice root D minus 1. Then he says, well, let's just relax this a little bit. We take this bound, we plus epsilon. We just fix this epsilon positive, no matter how small it is, just fix it. Then we consider the graphs, D-regular graphs, with the largest non-trivial eigenvalue is less than this relaxed bound. And he has shown that when the size goes to infinity, and it's with probability 1 that this thing holds. So, so this is the situation we see. If we relax this a little bit, then there are tons of them. Okay. So a very marvelous result this spring was that Marcus and Spielman and Srivastava has shown that there exists an infinite family of Ramanujan CD biregular bigraphs. Okay. So when C is equal to D, then we are looking at the D-regular graphs. So then they answer this question in the affirmative. Okay. For any C and D. Yeah. So I'm going to explain their work. Okay. So their proof is an existence proof. Okay. So the strategy is to show that if I start with a connected Ramanujan bigraph, and so show that any such kind of bigraph has a twofold cover, twofold unramified cover, which is also Ramanujan. So therefore, if I can start with Ramanujan graph, just one of them, then this theorem guarantees that I have twofold cover, etc. Then I will have infinite tower. Okay. So Now let's look at a special case. If we want, say, how about the CD regular by graph? So all we need is that I can start. If I can start with Ramanujan graph, then I will have a tower. So in this case, the bottom graph is trivial, is the complete CD regular by graph. That is Ramanujan. So we can get infinite tower. Okay. So let me explain a little bit. Okay. So if I start with the graph X, what is a twofold unramified cover? So that's very easy. You just take the graph and you just copy it. You reproduce it. Okay. So and you line up the say this is my X. So I just take 2 copies of this. Okay. So if I do nothing, then I have 2 disjoint copies of X, and that's not interesting. Okay. So I want to make it connected. What do I do? So this has to be a cover. So I choose any edge. For any edge downstairs, I have to say that what are the edges sitting above it. So the case 1 is that it's the same as before. So this is what we call the type 1. And case 2 is that instead of keeping the original edge, I swap it. I connect the top with the bottom with the top. So I swap. So these are the only 2 possibilities for each edge. So I call this type 1 and that type 2. So if it's a type 1, I give it a sign. I call that this SE equal to 1. If it's a type 2, I call that SE equal to -1. Okay. So if I start with the graph, how do I determine a twofold unramified cover? I have to say that each edge, how I'm going to do. I either have a sign +1 or sign -1. Okay. So in this way, so if it's all +1, then I have this disjoint situation. So in this way, you see that we parameterized all the twofold unramified covers by this sign. So this is what they call assigning. So to each edge, we associate a sign. Okay. So if I pick up a sign, so I have this twofold cover. And what is adjacency matrix? Its adjacency matrix actually can be written this way. As 1 is a diagonal block matrix, 1 is the adjacency matrix of the graph downstairs. And the other one is its twist. And the twist is given by the sign. Okay. So that means that in the UV position, if it's an edge, originally as adjacency matrix of X, I would have 1. Now I have sign of that edge, S of E. So this AS is just like you take the original adjacency matrix, you keep all the zeros, and those ones you change into +1 or -1, depending on the situation. Okay. So there's another way to see this, which I find is quite interesting. Okay. So if we give ourselves any graph, we can consider its universal cover. Okay. So we think of our graph corresponds to a curve, and the way we see curve is the curve is identified with fields. So then if you think of this graph, X corresponds to a field, then its universal cover corresponds to the maximum unramified Galois extension. Okay. So here I'm concerned with the zeta function of the quadratic cover, YS, and the zeta function of the graph downstairs. And that we know very well that from number theory, if we have a zeta function of a quadratic extension, that's a zeta function downstairs times L function of a character of the Galois group. Okay. Now it's exactly the same. So the zeta function upstairs is zeta function downstairs times zeta function associated to the character of the Galois group. The Galois group is the fundamental group of the graph downstairs. Okay. So in this case, this X can be any graph. Okay. So I talk about the zeta function for the regular graph. For any graph, it has exactly the same shape. The only difference is that for the d regular graph, I put a d -1. times U squared identity matrix. Now this is another diagonal matrix Q, which is the diagonal degree matrix minus identity. Okay. And for the twist, it has exactly the same shape, except that the middle one, which used to be the adjacency matrix now, is now this matrix AS. Okay. So this is another way to see the eigenvalues for the quadratic cover. Okay. So here, there's two combinatorists, Bilu and Lineal. They have a conjecture. The conjecture says that for any finite connected graph X, you can find a sign S such that all the eigenvalues of this of AS are bounded by the covering radius of the universal cover of this graph. Okay. So if I call this covering radius R, that means that you can find a sign such that all the eigenvalues of this signing AS lie in the interval from minus R to R. Okay. What the Marcus, Spielman, and Srivastava did is that they proved this conjecture, but halfway. They proved the upper bound. So they proved that, for any graph X, you can find a signing S such that all the eigenvalues lie in the interval from minus infinity to R. Okay. But if this graph you start with is bipartite, then all the eigenvalues are symmetric about the origin. So having the upper bound is the same as having lower bound. So then in this case, all the eigenvalues of AS will lie in the interval from minus R to R. So therefore, your graph will be Ramanujan. Okay. So all they did is to prove the half of the conjecture. Okay. So how did they do that? Okay. So you first, just randomly label the edges of your graph. Suppose there are m of them. And let's assume that this graph has n vertices. Okay. So what we want to do is that for each edge, I want to find a sign, whether it's a +1 or -1, okay, such that at the end, all the eigenvalues of this matrix AS will have absolute value. All the eigenvalues of AS, which we know are real, will be at most R, because I only want to prove the half of the conjecture. Okay. So before that, let's just take any choice of signings. So we compute the characteristic polynomial of this matrix. Let's call that Fs. So there's a polynomial of degree equal to the n, the size of the graph. Okay. And so we know that all such Fs has the same, they all have the same degree n, and each of that has real roots. So we call that real rooted. Okay. So then let me explain how they narrow down to find this signing S. So first, let's average it over all such kind of characteristic polynomials. Okay. So when you add them all up, you get a polynomial of degree n again. So this total sum here actually has a combinatorial explanation. So that polynomial is called the matching polynomial of this graph. And it's known that all roots are real, and also know that the largest root is bounded by the covering radius. So this is the work of Gauss law. Okay, so this is known. So what we are going to do is that I'm going to first find the sign for the first edge, after that find the sign for the second edge, etc. So I'm going to start from this, and I'm going to go down. Okay. So when I sum this over all the signings, I'm going to separate that into two pieces. Okay. The first piece coming from the sum of those where the sign for the first edge is a +1. And the other coming from those sign of the first piece is -1. So that's obvious. So I just separate into two pieces. Okay. And then important thing here is to show that after you divide into two parts, each piece, again, has all roots which are real. And another important thing to prove is that there's a common interlacing polynomial. Namely, there's a polynomial with degree m minus 1, and the roots of this degree m minus 1 polynomial separates the n roots of f plus 1 and f minus 1. Okay. If one can have these two properties, then for knowing that the largest eigenvalue of the sum is bounded by R, you can show that at least one of this, the f plus and f minus, will have real roots bounded by R. Okay, so it may be both have that property, but doesn't matter. We just choose one which has a real root bounded by R, and that sign is what we call the sign for the first edge. So we determine that. Okay, so now we go down. So I take this, f S1, E1, the sign we have determined, and then it's summing over all the signings where the first sign, the sign of the first edge, is given by this SE1. Then we split it into two parts, depending on the sign of the second edge, where it's a plus 1 and a minus 1. And again, you show that each piece has real roots, and they have a common interlacing polynomial. Okay, so therefore, one of them will have the real roots bounded by the largest root of the sum, and which is bounded by R. So then when you choose this gives you the sign of the second edge, and we continue this. So from total, and then we gradually, each time we do half, 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 and go down. Finally, we come up with a sign. Okay, so in this argument, there are two things which are important. One thing is to show that so somewhere in the middle, we have we divide the sum into two pieces. Each piece should have roots which are all real. Second is that they should have a common interlacing polynomial. Okay, so the existence of a common interlacing polynomial comes from a theorem by Fisk. Okay, so each time we have two polynomials, okay, they have the same degree, and we want to show that they have a common interlacing polynomial if all the linear combination of them by the real numbers between 0 and 1, okay, a times f plus 1 minus a times g, if all of them have real roots, then they will have a common interlacing polynomial. So therefore, all the problems are reduced to knowing when some kind of polynomial have real roots. Okay, so here is the key theorem, okay, how to show that polynomial has real roots. Okay. So to begin with, we have seen that if we add up all the polynomials of all the polynomials from all the signings, that thing has real roots, and we know that's bounded by R. Okay. So what MSS proof is that we show a similar thing like that, and which means the following. Okay, so I still have this polynomials, this Fs associated to all the signings. So they show that if for each edge, okay, so each edge there's a signing, either plus 1 or minus 1. So if we pick the signing of each edge with certain probability, with any probability between 0 and 1, okay, so if the signing is 1, it's probability pi, then the minus 1 will be the 1 minus pi. So if we pick up the probability of the signing of each edge independently, any probability, and we sum them, and this result is again, it gives a polynomial of real roots. Okay, so that's the key thing they prove. Once you have this, then their theorem holds. So I would like to end this and to go back to the comparison with the towers on the curves. So we have the Ihara bound AQ, which is the lim sup of the number of rational points over the genus as genus goes to infinity. Okay. So on the graph side, we have Alon-Bopana theorem, which originally was lim inf of the the second largest eigenvalue. So, so originally they showed that this thing, if you have infinite family as the size of the graph goes to infinity, it's greater or equal to the covering radius. Okay. So if we restrict ourselves to the biregular graphs where they have now shown the existence of the infinite family with the bound, Ramanujan bound, so actually now we have equality here. So this covering radius plays the same role as the Howard's constant, AQ. Okay. We have seen that for a very special kind of Q, or special kind of the valency, we have the infinite tower constructed using modular curves or modular forms, etc., which is similar on both sides. Okay. So what's special about the Ramanujan graph is that, so I'm doing this for the lim-inf. Okay. So this interval is for the interval for the spectrum for the universal cover. Okay. The Ramanujan graph is that those graphs which lambda 2 are on the left-hand side. Okay. And we find the infinite family which goes forever, so that we approach this R from the left-hand side. Okay. And for the towers, I'm not sure. When you have an infinite family, whether you approach that from the left-hand side or from the right-hand side. You mean from the smaller and the gradually bigger, or the bigger? So this is your AQ. So are they bigger than this AQ? Or bigger than AQ and then graduate. So that's very similar to the Ramanujan graphs. Your infinite towers is exactly like what happens to Ramanujan graphs. Ramanujan graphs from the left-hand side, because this is lim-inf, okay. And this is lim-sup, so it's a bigger approaching this AQ. And on the graph side, when you have this infinite family, the MSS approach is that they consider unramified covers. Okay, so for the unramified covers, it's sort of really like if you consider unramified covers, then you know how genus grows very clearly. So the unramified cover towers they consider really is sort of like the class field tower, because of unramified extension, and each time is degree 2 class field towers. But here we know that occasionally we have class field towers, but the difficult part is to control the growth of genus. But if we have unramified towers, then we know. So if you say also fix the degree, say quadratic degree, then we know how the genus grows. Then the question is really, to splitting the points of degree 1, how it splits. And how to split points of degree 1 is exactly which corresponds to the choice of S, the sign. Because we know that for the quadratic extension, they are determined by the primes, which splits completely. In the case of graph, there are infinitely many primes that will split completely, just like in general. But since the objects are finite, they are determined by finite many situations. So from that sense, the family of Ramanujan graphs is very similar to the family of towers. Okay, so that's all I want to say. Thank you very much. May I say one thing? Okay, I put a question here which I forgot to say, because for the towers of the curves, well, we know that there's explicit families. So here the MSS proof is existence proof. But so I'm wondering whether there's a way to determine how to choose the signing, whether there's an algorithm, how to choose signing. So to make it explicit. Okay, thank you.
Are there questions or remarks? I have a remark.
No, you should use this, I was told.
Well, I'll try to. Well, I have a remark, which is that for curves, we work with odd cohomology, while for the graphs, it is in the denominator, and we work with even cohomology in some sense. And
No, it's...
No?
No.
Because I think that's the reason why for Ramanujan graphs we have 2 square root of d minus 1, while for curves we have square root of q minus 1, which is because of the Hara trick that when you square, you change the sign. And therefore, it might be reasonable to consider not curves as an analog, but surfaces with 0 h1. And there the analogy might happen to be more strict, but I'm not quite sure.
The Hara's identity that I showed there can also be proved using combinatorially using cohomology. And it's really H0 and H1 which comes in. So, so the denominator is appears in the H1 side. And the numerator is, this 1 minus u squared part comes. Anyhow, it's H1. These are 2 root d minus 1. I think probably would be most transparent when you look at this biregular case. If you separate the c and the d, you have root c minus 1, root d minus 1. When c is equal to d, you have twice root d minus 1. So if you becomes half for the biregular one, for me, that the 2 is because c is equal to d.
Other remarks?
But I think your comment is good, so that one should think of from the surface. But maybe that when we will hear from the next 2 lectures, when they talk about the Drinfeld modules, I think they do the module of rank more than 2, right? Or it's only rank 2? Do you use higher rank? Yeah, so higher rank means it's actually more than surface. Yeah.
Any other contributions? Obviously not. Then let's thank Winnie again.
Thank you.